to your school name and then your initials, if you would, please. And if you haven't joined already, you could go to joinpd.com and enter this code. If you lose this code, it'll be in the upper right-hand corner of the shared screen as we go through. But Pear Deck, the pd.com, allows you to kind of like answer some questions and stuff like that. Keep in mind that no one knows what you answer. So when I see all the answers, no one knows that it's Anabarky. No one knows that it's Buckhorn High Ashley. No one knows it's Logan Crouch. So answer away with whatever you think it is. There's no shame because no one knows what you answer. Okay? So the goal here is to review Unit 1 tonight. So as we go through, I'll be explaining stuff. If you end up with questions, please feel free to throw them in the chat box. And if I don't hit the chat box, feel free to unmute your mic and say, hey, Captain Awesome, can you explain that one more time? So my name is Danny Elegante, and I taught at Bob Jones for 14 years. I taught for 27 years total, and COVID told me that this was a good time to review. I mean, not time to review, to retire. So all we're going to do tonight is just review Unit 1, right? So this is a good time for you to kind of check off, what do you know about Unit 1 in AP, and what do you not know? So what do you know about the atom? So Unit 1 is all about the atom, periodic trends, what does the periodic table tell us, and those kinds of things. So the atomic number for oxygen is 8. So right away in Pear Deck, I'm going to ask you, what does the atomic number tell us about the atom? So in Pear Deck, go ahead and just type out your response. What do you think the atomic number tells us about an atom? And if you haven't joined Pear Deck yet, you just go to joinpd.com and you enter that code KQISIV, and you too can take part in the fun. So I've got 31 responses. Y'all are doing great so far. If you're not one of the great ones, if you're not one of the 37 in, then you definitely want to join pd.com and enter the code that's in that upper right-hand corner. Let's see what some of y'all said for an answer. Let's see what your answers are. Keep in mind, I have no idea who you people are. So Anabarky, you still need to change your name to your school name, and then AB. But we're going to keep calling your name because it's there. So I don't know which one of these answers is who. So feel free to answer without fear of getting it wrong. How many protons, and electrons in the neutral atom? If you'd put neutral, I'd be okay with that. Because remember, things can be ions, so it's kind of hard sometimes to say how many electrons, but that's a good answer. Protons. Look at those. That's great answers. Number of valence electrons. All right, that right there is not okay. The atomic number tells us the number of protons. It's the identification badge for an atom. The atomic number is how many protons there are. The mass number is the number of protons and neutrons together. So by and large, y'all are getting its number of protons, but y'all definitely need to know that the atomic number tells you how many protons something has. All right. So with that said, those are great answers. So let's keep going. So what does mass spectrometry tell us? Well, a mass spectrometer is something that tells us about the nucleus, right? So it's telling us something about what makes up the nucleus of an atom. So you'll see in this graph for copper, you'll see two peaks. One is copper 63 and one is copper 65. Now that 63 is not the number of protons. That 63 is the mass number, the number of protons and neutrons together. And that 65 is the number of protons and neutrons together. So remember, copper always has the same number of protons, but it can have different number of neutrons. And what those neutrons tell us is, oh, by the way, this is an isotope. So mass spectrometry is all about isotopes. So how many isotopes do you see? According to this graph, 2. Which one of those isotopes is found in greater abundance? Well, copper 63 makes up about 69 or 70% of all the copper that we find on the Earth. And then copper 65 makes up the other 31%. Now, how do we find the average atomic mass of copper? Well, this goes back to, we take the mass, 63, times the percentage, 0.69. And then we take the other isotope, the 65, times the 0.31. And once we get those two answers, we add them together. So mass times percent plus mass times percent. You do it for every single isotope and you add up all the numbers. And that's how we get that average atomic mass that we actually see on the periodic table. So you'll see a problem like this on the periodic table. So let's give it a quick read. The average atomic mass is 20.18. There are 2 common isotopes. The isotopes are 20 and 22. And the 2 masses of those isotopes are given. And the question says, calculate the percent abundance of each isotope. And then it says, calculate the number of Ne22 atoms in a 12.55 gram sample of naturally occurring neon, right? So we've got a couple things going on here. And so how would you go about figuring these kinds of things out? Well, along with that part II, where it's saying how many atoms are there, is that concept of a mole. And if we're going to talk about a mole, then we also need to talk about empirical formulas. An empirical formula is just the simplest whole number ratio of elements in a compound. So if you have C1H2O1, then the ratio is fairly straightforward, right? If it's C6H12O6, that's not simplified. It would simplify down to C1H2O1. I can guarantee you that there will probably be at least one of these questions on the AP exam. And the trick here is to go from grams to moles, and then take the number of moles and divide each one by the least number. So you can see that when I changed it to moles using molar mass, what I do is I divide each one of the answers of moles by the smallest number of moles. And what that does is simplify my ratio. It becomes a 1:2 ratio. So to find an empirical formula, very important that you realize, oh yeah, I got to be able to go from grams to moles. So my mantra for y'all, for all of these review sessions as we go from here until May the 7th, is when in doubt, mole it out. A lot of times you can make major headway on a problem by just changing the grams of something to moles using the molar mass on a periodic table. Once you have the empirical formula, you can also do what's called the molecular formula. That's also something that's in Unit 1. So it becomes a Gazinta problem. So the empirical formula, you're given C3H5O2. The molecular mass is 146. So the molecular formula is just some whole number multiple. So it could be C6H10O4, or multiply it by 3, C9H15O6. That's going to be the molecular formula. So if we take the molar mass and add it all up, C3H5O2 adds up to 73. And then how many times does 73 go into 146 is 2. So to do this molecular formula, we would take C3H5O2 and multiply everything by 2. And we'd get C6H10O4. Now, y'all did that in regular chem. You should have done some in AP, but just keep in mind some of those simple things, some of those small things on that you'll find on the AP exam. You just got to go back and review them. And once you got them forever, because it's just a skill. So if you feel like you don't understand it, you could also bring it up to your teacher. Hey, do you have some empirical formula or molecular formula problems that we could work for practice? All right. So empirical formula, molecular formula, and the mole. So what I'd like you to try to do is just try to answer part I and part II, if you would. Go ahead and just take a stab. How would you go about answering part I and part II? And you can just type out your response. If you don't know how to do part I, that's okay. Totally okay. And if you don't know how to do part II, that's okay as well. But you ought to be able to do one of them. So if you only feel like you can do part II, then do part II. If you don't have one yet, you may want to open up a tab and just Google periodic table. My favorite is webelements.com. Or if you have a periodic table that you want to look at, hopefully you can drag that out. And if you need to grab a calculator, feel free to do that. But this is an example of a free response question. And the free response questions, you get calculators. And so I just wanted to give you all, take a stab at part I and part II. Take your time. I'm going to give you a couple minutes. I always tell my students the best way to miss a free response question is not to answer it at all. Just so you know what it's like when they sit down to grade these papers, typically they do it in person, but in Salt Lake City. This year it'll all be virtual, but the rubrics are very carefully crafted to give points for good chemistry knowledge. So sometimes you can get a point for not quite answering the question correctly, but for doing things like changing grams to moles, right? So just take a stab based on your knowledge of the mole and on part II, and for the percent abundance, just take a stab. You may remember doing a lab like this in just regular chemistry that involved pennies. You may have done a lab called quinium or isotopic pennies, and this is very, very similar. And when I show it to you, you're going to be like, oh, yeah, I know how to do that after all. But the year they asked this was pretty tricky. And so if you're not ready for it, you know you're going to miss it. But part of the thing here is, as we're reviewing this stuff, is to kind of remind y'all of some of that simple stuff from Unit 1 from oh so long ago. All right, we got 21 of 53 responses so far, so good. All right, so I'm going to give you all like 1 more minute to take a stab with what you know. Part I is harder than part II, so if you just want to take a stab. The other thing you might want to drag out is, if you have it, is the AP, not the, of course you need a periodic table, but the reference sheet. So if your teacher is giving you the reference sheet, it's got like a bunch of equations on it and a bunch of constants and stuff like that. Just looking at that sometimes will help you remember how to do things like Avogadro's number and those kinds of things. I'm just going to peek at your answers real quick. Keep in mind, I have no idea whose answer is whose. Looks like I've got some good answers so far. There's some really good work that you're seeing on the shared screen. Somebody's getting fancy typing in colors. I like it. I like it. So some of y'all are finding moles, which is a good way to get started, but just don't forget that it wants to know how many atoms there are, not necessarily how many moles there are. All right. So somebody said not sure. That's a totally honest answer. That's great. So what I want you to think about is, as we go through these review sessions, if you know how to do every single thing, then I'm really not doing anything for you. So the key here is, when you run into a concept like calculate percent abundance, maybe you write that down as something that you need to work on as you head into May the 7th, when the AP exam is, or in May when the AP exam is, depending on when you're going to take it at your school. And then if you know something really well, also create a list of things I totally rocked, right? I totally know what I'm doing. So that you kind of create a list of stuff I need to go back and look at, and a list of stuff that you totally know what to do. So let's go ahead and look and see, for that first part I, how you would actually do this. So whenever you have just 2 isotopes, you can create a problem where one of them is going to be X, X percent, let's make it. And the other one is going to be the other part. So if X is 40%, then the other isotope has to be 60%. Or if X is 10%, then the other isotope has to be 90%. So X is going to be the percent that is the 19.99 in this particular thing, right? So remember that when we do percentages, we have to move the decimal place over. So it's not 100 minus X, it's actually 1 minus X, because 2 percentages add up to 100%, or 1, once we move the decimal place over. So the key here is to make one of them X and the other one 1 minus X, the other percentage. And then it just becomes a do the math, do the algebra, solve for X, and you get the neon 20 with a mass of 19.99 being 90.5%. That means the neon 22 has to be the other 9.5%. Now, what I've asked you to do in the pear deck is just give me your honest assessment. I knew what I was doing, I kind of knew what I was doing, or I just really had no idea what I was doing. And remember, no one can see your answer, right? So let's see. I've got 3, I totally knew how to do this. I got a bunch of, I didn't have a clue. And several of y'all that says I kind of knew how to do this. And that's kind of what I was expecting. You know why? Because AP chemistry, some of it's not hard, but some of it's been a very long time ago, right? So for those of you who like, I kind of knew how to do this, totally expected, because you haven't done this in a while. And it's just something you want to kind of go back over and look at it. Abigail, you asked, is there any reason which one is X and which one is X minus 1? Nope. Whichever, you can make X be whatever it is. Or if you don't want to talk about your X's, then you can just pick another letter. One can be K and one can be 1 minus K, right? So don't forget, you can always go back and ask your teacher, hey, do you have a problem like this that we could work again? A lot of y'all did this in just regular chem or pre-AP or honors chem, and you've just forgotten about it. And that's totally okay. Now let's go on to this other part II. This is how you calculate the number of nitrogen or neon 22 atoms. So first thing we do is change grams to moles. So the molar mass of neon is 20.18, and we would get that off of the periodic table. And then the trick here was knowing that 95% of them, or sorry, 9.5% of them were neon 22s. And then multiplying it by 6.022 times 10 to the 23rd. So there was a wrinkle in that question. And my guess is that most of y'all who wrote down how many nitrogen 22 atoms, you didn't think about, oh, I need to multiply that by that 9.5%, right? Well, here's what I want you to realize. If you got the correct molar mass, so when you change grams to moles, if you had used the correct molar mass, you would have gotten 1 point. And you get 1 point for knowing that it's the correct fraction. That's what that 0.095 moles per 1 mole. You also could have just written times 9.5% in your work, because out of all the neon atoms, neon 22 was 9.5%. And then you had to multiply it by Avogadro's number. Now, Avogadro's number is not something you need to memorize. Avogadro's number is given to you on the AP reference sheet. And if you haven't ever seen that, you may want to ask your teacher for that. Hey, do you have a copy of that reference sheet that we get on the AP exam? Because y'all need to know going into battle in May on the AP exam, what do you need to know and what stuff is already given to you, right? So there were some tricks here, but just realize that this one question was worth 3 points, but you could have gotten 1 point just by changing grams to moles. All right, so that was kind of a tough question, but that's kind of the thing in Unit 1, where we're talking about just the mole concept, right? We're talking about empirical formulas. And if you came to the review sessions in the fall at all, then you saw a lot of those empirical formula problems. And I'm sure your teacher, when they start reviewing with you in April, will, or earlier, will actually be pulling out some of those empirical formula problems. Sorry, my bad. I've also asked you to respond on this question, how you felt about it. So I kind of knew how to do this, I totally knew how to do this, or I had no idea how to do this. And I'm getting a kind of, I kind of knew how to do this. And that's because largely most of y'all, when I looked at your answers before, were forgetting about that. Not all of the atoms are neon 22, only 9.5% of them were neon 22. Now, here's the beauty. If you had said neon 22 was 50% in problem number 1, and then you had used that 50% in problem II, they would have given you credit. So whatever percentage you had in part I, if you had used that in part II, they're not going to do what's called double jeopardy. Just because you miss the first part does not mean that you'll miss automatically the second part. So don't be afraid to pick up the answer that you use and go with it, because again, it's all about assigning points for really good chemistry knowledge. All right, so the other part of this is now that we've talked about the nucleus, right? So we talked about mass spec, how many protons are there. We can also do electron configurations. So just a brief reminder, the blue part of the periodic table in front of you that's on the Paradex slide, that's the S section, and S holds 2 electrons. And the yellow section in the middle, that's 10 blocks wide, and that holds 10 electrons. The P section over on the right-hand side holds 6 electrons, and then that one at the bottom is F. And very rarely do we do anything with electron configurations, but sometimes you see it. But electron configurations are super hard the first time you do them in regular chem. And then you're like, this is the easiest thing in the world. So just keep in mind that you're going to need to be able to write electron configurations. And you're also going to need to be able to write electron configurations for ions. So for example, magnesium has a certain number of electrons, 12. But the magnesium ion, because it becomes a +2 charge, does not still have 12 electrons. It only has 10. By the same token, the oxygen atom has 8 electrons, but the oxygen ion has 10 electrons. So we have to keep in mind, sometimes we do electron configurations for regular atoms, and sometimes we do electron configurations for ions. The other trick to this is, which one do they want? Well, sometimes they'll say orbital notation, and that's one where you've got arrows going up and arrows going down. Sometimes when they say electron configuration, they'll take a noble gas configuration where you pick the noble gas that comes before the element. So let's say we are doing strontium. The noble gas that comes before strontium is krypton, Kr. So we would write krypton in brackets, and then we would write 5s2. So that's a shorter way rather than writing 1s2, 2s2, 2p6, all those kinds of things. But sometimes AP exam will give you a big element, something like SR or FL or gold or lead or polonium or something like that. And they don't want you to write 1s2, 2s2, because nobody got time to read that. So instead, they'll say, give me the valence electron configuration. And the valence electron configuration is just the outermost electrons. So polonium, if on the screen in front of you, that would be the 6s electrons and the 6p electrons. And it would be the 6s and the 6p because that's the 6th energy level. We don't include the 5d because the valence shell are the electrons that are in the outermost energy level. So if we were going to do the valence electron configuration for polonium, we would only include the 6s ones and the 6p ones. All right, so make sure you're reading the question to know what's going on. All right, so here's a problem on the AP exam, okay? Write the electron configuration for a zinc atom in the ground state. So you may need to run over to your periodic table and find zinc. And then go ahead and write what is the electron configuration for zinc. And then for part II, I want you to go ahead and answer that as well. Which sublevel are electrons removed when a zinc atom in the ground state is oxidized? And oxidized, remember, is when you lose electrons. So basically, when zinc loses electrons, which electrons will be removed? Now, keep in mind, a sublevel is not just energy level. So the answer can't be 3. it has to be 3s or 3p or 2p or 6s or 5f or something like that. So it's got a number that shows the energy level, and then either S, P, D, or F. Those are the sublevels that we put electrons in. So we've got 36 answers so far, which is great. And if you're wondering what ground state means, ground state just means the electrons are all where they're supposed to be. The electrons haven't gotten excited or lost or anything like that. All right, I'm just going to peek at your answers real quick, see what we got. And I know you can't really type exponent, so no one's going to bust you on that. Seeing lots of good answers. Looks like y'all really know your electron configurations. That's good. All right, so the person that wrote argon 3d9 4s2, it says write the electron configuration for a zinc atom. So maybe that's okay, or maybe they want the whole one. We'll know in just a minute when we look at what the rubric asks for. Okay, looks like really great answers. And I know it's hard to type exponent, so whatever y'all write is fine. I can read it, trust me. All right, so let's see what the answers actually were. So the electron configuration was either the one on the left or the noble gas configuration. So for those couple of you who did noble gas configuration, totally okay, right? You're showing good chemistry knowledge. And then when we remove electrons, some of y'all said 3D, but the key is you're always going to remove electrons from the outermost energy level first. So you're going to pull the 4s electrons because they're farther away from the nucleus than the 3d. So zinc takes on a charge of +2, and that's because it loses those two 4s electrons, right? So when we write an electron configuration, it's not just in order to write it for funsies, it's to tell us something about the atom, just like we can tell something about the number of neutrons in an isotope or the number of protons in the middle of the nucleus. Now, I asked y'all to answer a question here, and the question basically said, how many points did you get for this or anything like that? Springville, Caitlin, if you wrote 4s2, you would get the point. Yes, because you're saying 4s. You're totally good. All right, so I'm just going to peek at the answers real quick. A couple of y'all got no points. A lot of y'all got 1 point, and a lot of y'all got both points, the 2 points. So the key here is, well, I only got one of the 2 points. Well, you got half of the points available for this question. So this question that year was actually a 4-point question. So you're only seeing 2 of the points. So if you can get one of the 2 points and then pick up another 2 points on another part of the question, then you're really doing pretty well. Donahoe, if you said 3D10 and then 4s2, that's acceptable as well. EP Oxford totally varies. There is no way to say one way or the other how much this is. If I would know that, I would sell all of my knowledge and become a very rich man. I'll put it that way. All right, so the PES is where we get this information from. So PES stands for photoelectron spectroscopy, and we fire X-rays at samples of elements, and then it tells us something about the electrons. So before you go in, if you look at the shared screen that I'm sharing with you on the Zoom call real quick, I just want to show you what the photoelectron spectra look like. So if I looked at helium versus hydrogen, so there's hydrogen, it's got one little bump. Helium's got a higher bump. So the higher the bump, the more electrons there are. The energy at the bottom is an indicator of how much energy it took to remove those electrons. If I click on beryllium, beryllium's got a 1s electron here at the 11.5. Those are the 1s electrons. And then the 0.90 are the 2s electrons. Now, how do I know that the 1s electrons are the 11.5? Well, the closer electrons are, because they're in the 1s, the closer they are to the nucleus, the stronger the attraction between protons and electrons are. So the closer you get to the nucleus, the harder it is to remove those electrons. So I know that the 1s has a greater ionization energy than the 2s. That's how I know the difference there. If I clicked on carbon, the 1s is 28.6, the 2s is 1.72, and then the 1.09, what's that? Well, when we do electron configurations, it'd be 1s2, that'd be the 28.6, 2s2, that'd be the 1.72, and then finally 2p2, right? So we can get an idea of all the electrons in an atom just by shooting X-rays to it. And then all we have to do is analyze the data. You don't have to understand how the machine works. You just have to analyze the data. So you can look at something like this and you're like, yeah, but how do I know which one's which? Just pay attention to which ones are going to be attracted the most to the nucleus, right? So if you go back to the pear deck presentation, what I want you to do is you ought to go ahead and be able to drag icons. You ought to be able to go ahead and drag icons. The blue one to where you think the 1s electrons are. Drag the purple icon to where you think the 2s electrons are. And drag the green icon to where you think the 3s electrons are, based on what we just said. Okay, y'all are great so far, 46 out of 56. All right, let's kind of get an idea of where y'all are dragging these. So blue to the 1s, purple to the 2s, and green to the 3s. Looks like most everybody is getting it right. The key here is the 1s electrons are going to have the greatest, what we call ionization energy, the energy necessary to remove those electrons. So the 1s would be the mark at 239. The 2s would be over here at 22.7. And the 3s would be over here at 2.05. Now, why is the number getting smaller? Because every time you jump from the first to the second to the third energy level, you're getting farther and farther away from the nucleus. And when you get farther and farther away from the nucleus, there's less of an attraction. So that's why that goes down. So PES tells us something about the electrons in an atom. So here is a PES spectrum, and let's see if you can identify who you think this element may be. So just look at this and look at the periodic table and think, what element might this particular spectrum be? And you can just draw, oh, sorry, my bad. You can identify the elements, but also since you're able to draw on this one, if you could draw like what the peaks are. So here at 40, is that the 1s or the 2s or what is it, whatever is it? And over here on these two peaks on the right, if you could just draw what electrons you think those things stand for. I forgot what I was doing. Sorry, my bad. I need a drink of water. I noticed somebody said they liked my hat. If you come back every week, I'm going to be wearing a different hat every time. So this time I tried to get, just keep it simple. Just be a cow and have some horns and try to milk this for all it's worth. So I've got 42 answers. Let's see what some of y'all's answers are so far. Okay, somebody said nitrogen. Yes. 1s, 2s, 2p. Somebody likes to type. I know it's hard to draw with your mouse. 1s, 2s, 2p. Also realize in this Pear Deck thing, you can totally change colors if you want to. Here's a blue one. Looks like really good. Okay, somebody loves nitrogen with a smiley face, loving it. Okay, so some of y'all are putting neon and some of y'all are putting nitrogen. I've seen a couple 3Ps. The problem with having so many people on a Pear Deck is it takes me a while to scroll. So I'm going to go down to the bottom real quick and look at some of those answers. Whoosh. 1s, 2s. Okay. Nitrogen. All right, cool. Y'all have some great answers. Okay. So the correct answer here was nitrogen. Now, for those of you who said it was neon, here's what I want you to realize. This peak at 40 is 2 bars high. Now, we know the 1s holds 2 electrons. So that means each bar represents 1 electron. So this first peak is 1s2. It's 2 lines high. This second peak down here between the 5 and the 0 is also 2 electrons high. So 1s2, 2s2, and then this last peak down here at the end is 3 bars high. So those of you who put 2p6, remember that a PES graph, the height of the peak tells you something about the electrons. Donahue, Sam, it doesn't really matter which. The idea was, can we just label them or whatever? Thank you, Mr. BB Comer. I think I know who that is. He's probably wearing an Auburn shirt of some kind. All right, so take a stab. Actually, let me skip this one real quick. All right, so let's take a moment to talk about periodic trends. So a lot of people are taught periodic trends is super easy. You just, it's up and to the right or down and to the left and things like that. But the AP exam is really going to ask you to think about periodic trends. And so periodic trends is really all about Coulomb's law. So when we look at atomic radius, yes, the radius decreases as you go to the right. Totally fine. The radius increases as you go down. And maybe sometimes in another class that would be enough of an answer. But for example, they're going to want you to say lithium is bigger than neon. And not only do I know that, but I also know that this is the reason, right? So what actually talks about and governs all those periodic trends? Things like atomic radius, ionic radius, electronegativity, electron affinity, and ionization energy, all the periodic trends. It's all about Coulomb's law. So Coulomb's law is not given anywhere on the AP exam. They don't give you this equation because they don't ask you to actually calculate anything. So Q1 in Coulomb's law is the positive charge. Q2 is the negative charge. And R squared at the bottom, that just means radius. So it's all about the charge and how far away they are. And believe it or not, this is exactly what we were talking about before when we talked about, oh, the electrons that are farther away have less of a force of attraction. So when we were talking about the PES diagrams, the greater the distance between the nucleus and the electrons, the less the force of attraction. So less energy to remove it. The Q1 and Q2 is also going to come into how many electrons do you have and how many protons you have. And the general rule is this. You look at the electron configurations. You look at the number of occupied energy levels. So when you're comparing two things, you have to think about the electron configurations and who has more layers of electrons, who has more, layers of stuff. Whoever has a greater distance, that's much more important than charge. But what happens when two things are in the same row? So for example, oxygen and fluorine. Well, they both have two layers of electrons. They both have electrons in the 2s and the 2p. So how do we decide when, oh wait, what am I supposed to do when they're both in the second energy level? That's when it comes down to protons. Because protons have a positive charge and protons' job is to attract electrons. So the more protons you have, the more a pull on those electrons you have. So I'm just going to show you this. If you look at the Zoom screen that I'm sharing with you, this is just a very simple description of how Coulomb's law works, right? So I have Q1 and Q2. Q1 has a charge of negative 2, and Q2 has a charge of 8. So there's that force of attraction. Well, what if I made charge 1, Q1, to be negative 8? Well, now there's a greater force of attraction. There's a greater positive, negative attraction, right? But notice what happens when I move these suckers apart. The farther apart they get, the less and less a force of attraction there is. So as long as you know that the farther away there are, the less the force of attraction, and the more protons something has pulling on the electrons, the greater the force of attraction, then you can do any periodic trends because it's asking you to think really hard. Okay, so let's look at this sample question. Which one has a higher first ionization energy and supplies the best justification? So you'd have to go to a periodic table. You would have to find BR and KR and try to come to some decision who has a higher first ionization energy and which one gives the best reason for it. If all you knew was like to the right and up or things like that, then you wouldn't know the reason behind it. And that's what we're asking you to do in Unit 1 is show that you have an understanding that protons attract to electrons. And that has everything to do with how easy it is to remove those electrons, where those electrons are kept, and how that influences how something reacts. Right? So this one, you would look and go, okay, how do I answer this kind of question? Then you would go, okay, well, bromine and krypton are both in the same row. If you look on, they're both in the same row, right? So which one has a greater ionization energy? Well, since they're in the same row, they both have the same number of layers of electrons. Well, if they both have the same number of layers of electrons, then it becomes about protons. So who has more protons pulling on those electrons? Is it bromine or is it krypton? And if you look at the periodic table, krypton has more protons than bromine does. So since it has more protons, then it has a greater first ionization energy. It takes a greater amount of energy to pull away an electron. So a lot of people say, oh, it'd be krypton because its valence shell is full, or because it's a noble gas, or because it doesn't need any additional electrons. All of those are true statements. It does have an octet. It does have 8 valence electrons, but that has nothing to do with ionization energy. They just happen to coincide. So the key here is, do you have an understanding of why it is? And the correct answer here would be D, krypton, because it has more protons. All right, so let's say we're doing this. Who has a bigger radius, calcium ion or sulfide ion? So first, we'd write the electron configuration for calcium ion. So here's calcium ion. It's right here. It's got 20 electrons, but it's calcium ion. Calcium ion loses 2 electrons. So we need to write the electron configuration not for 20 electrons, but for 18 electrons, because it's got a +2 charge. So this is the electron configuration for calcium with a +2 charge. The next thing we would do is write the electron configuration for sulfur with a -2 charge. So again, we'd go to the periodic table. Sulfur has 16 electrons. And then when it becomes an ion, it gains 2 electrons because it has a -2 charge. So sulfur with a -2 charge has 18 electrons. So we write the same electron configuration. The word for that is isoelectronic. They both have the same electron configuration. So now, since we know the layers of electrons is the same, they both have 3 layers of electrons, occupied energy levels, then we need to look at the number of protons. So calcium has 20 protons and sulfur has 16 protons. So between 20 and 16, who has a greater pull on the electrons? Well, calcium. Calcium has more protons. Well, if you're pulling harder on those electrons, that makes your radius smaller. That's why when we looked at the slide of radius and it got smaller as you went from left to right, the reason why it got smaller is as you go from left to right, you're getting more and more protons, which pulls on that cloud of electrons just a little bit tighter. So you only worry about protons when you have the same number of occupied energy levels. If it had been calcium ion and something else, where maybe it had more layers of electrons, I wouldn't worry about protons at all. I would only worry about number of layers of electrons, right? So I could have done calcium and strontium. Strontium would have been bigger because strontium has more layers of electrons. All right, so see, go ahead and take a stab at explaining the trend in atomic radius for me. The 20 and the 16. Okay, let's see. We'll go back and answer some of y'all's questions. EP Oxford, you really need to say it has more protons and that gives it a stronger attraction. If you just say stronger attraction, I don't know. Maybe it thinks the electrons are hot. I don't know what you mean by stronger attraction. So you really need to put together that you know more protons means stronger attraction. Is it required to write out the electron configuration on the AP exam? Anytime, and this is Elizabeth, anytime that the AP exam says explain, then what they're asking you to do is claim evidence reasoning. So we're claiming that this one has a smaller radius. My data is my electron configuration. So you also could have written it as a noble gas configuration, but if you want to make sure you get the point, then yes, you would probably write out the electron configuration because you're trying to tell the reader, hey, I know where the electrons are and how that affects the size. And TC Oxford, the 20 and 16 came from the atomic number. So calcium had an atomic number of 20 on the periodic table, which means it has 20 protons and electrons in the neutral atom. And sulfur has an atomic number of 16. That's where I got those from. All right, so let's see what some of y'all's answers are to the trend that you see in the atomic radius. And notice B, C, N, O, F, and Ne are all in the same row of the periodic table. Okay, so just to point out that y'all's answers are good, but they could be a little bit better. Atomic radius increases when there are more energy levels and decreases when there are more protons. Now, the first part, increases when there are more energy levels, has nothing to do with this question because they're all in the same row. So including that piece of information doesn't really help you explain your answer. The other part that you're missing is why does it decrease when there are more protons? The second answer, if there are more protons, it has a stronger attraction, which means the radius would be smaller because there's a greater amount of protons pulling the electrons. Okay, and again, all I've asked you to do is just atomic radius. So those of you who are hitting both parts, kind of concentrate on the question that's there. So some pretty good answers, all in all. Let's go ahead and obviously you were right. As you go across the periodic table in this data table, you're adding more and more protons. The more and more protons causes there to be a greater pull force of attraction on the electrons. That's why it gets smaller. Now, go ahead and take a stab at explaining the trend in ionization energy. All right, let's see. I'm going to scroll down to the bottom this time. Start looking at the answers there. Okay, saying you're going more up and to the right. Keep in mind that in that data table, all of those elements are in the same row. So there is no up. It's just left to right. I'm still here. I'm reading y'all's answers. So the atomic radius trend, Huntsville High, MJ, is that as you went from boron down to neon, you got more and more protons, and that greater number of protons means a greater pull on the electrons. The greater pull on the electrons makes that cloud smaller and smaller because you're kind of pulling that cloud of electrons closer to the nucleus. All right, so I want y'all to be very careful that when you name drop, like here's an answer that says, as the effective nuclear charge increases, you want to make sure that the reader knows that you know what that means, right? Just name dropping effective nuclear charge sometimes is not quite enough to get you the point. So just be wary and be willing to go, okay, let me explain that a little bit better. So effective nuclear charge is a fancy way of saying you have more protons pulling on the electrons. So why does the trend increase in general? From boron to neon, why does the first ionization energy increase? Because as you go from just a few number of protons to a greater number of protons, you're getting more and more pull on the electrons. the more and more pull on the electrons means they're going to be harder and harder to remove. Because remember, ionization energy is how much energy does it take to remove an electron. That's what PES does. It removes electrons. So the first ionization energy is the energy to remove one. So as you go through these elements, the greater ionization energy is because there's more protons pulling on those electrons. Now, what I want you to notice is they could have given you data that asks you not things that are in the same row, but instead things that are up and down from each other. And then instead of talking about protons, you would want to talk about, you know, the farther away the electrons get, the less of a pull on the electrons from the protons. And the less the pull on the electrons, the easier it is, the less ionization energy it requires. Springville Caitlin, Zeph is a fancy way of saying effective nuclear charge. Z is called the proton number. Z is the symbol for how many protons you have. So Zeph is just a fancy way of saying how many protons you have pulling on those electrons. What is the effect of the nucleus? All right, see if you can take a stab at how many valence electrons does this element have. So look at the data and you can just enter a number. Does it have 1, 2, 3, 4, or 5 valence electrons based on this data that you see? And I know it's 8 o'clock and I am almost done. We've got a couple more things to go over. So if you need to go, that's fine. If you want to stick around, we're probably to be in, I don't know, another 5 minutes or so. Carol, hi, Ozark teacher. In general, yes, the oxygen did have that goofy, it went up and then down and then back up again. For that general question, explain what's going on, I would not expect students to answer it because they'd have to go in this really long drawn out one. The AP exam would specifically say, explain why oxygens is different from what you expect. But that's a good thing to point out. All right, so let's see what y'all are putting. Okay, somebody put 15, can't beat that. All right, so I got a bunch of 3s, a couple 1s and 2s. So let me show y'all how to read this data so that you have an understanding. You're looking for at what point does the energy that it takes to remove an electron, at what point does it become ridiculous? So you've got one electron takes 577. That's fine. The second electron takes 1800. The third electron takes 2700. So you're looking at like, okay, I kind of see a trend there. And then the fourth electron takes 11,500. So that's a huge jump between the third and the fourth electron. So what would cause this huge jump? This huge jump would be because we have moved from the first, second, and third electrons were in the valence shell. So they were in the outermost occupied energy level. And then when we took off the fourth electron, it took a lot more energy because that was in a lower energy level. So it was something closer to the nucleus. So you have to look at what point does it become ridiculous? Oh, at the 11,577. So this thing must have had 3 valence electrons. Donahoe, Sam, you do not need to use special terms. It's okay to say things like, the bigger number of protons causes a greater pull on the electrons. Right, so this thing would have 3 valence electrons. Right, so this is not PES, this is that mass spectrometry. So I just want to say, can you try to figure out who this element is? So take a guess is. Northridge, Anna, You can pay attention to which one is more abundant if you want. That kind of helps you figure out. I got 31 answers. I got ZR. Thank you, Captain Awesome. Thank you. Zirconium, niobium. All right, so a lot of great answers. So, you know, for the purposes of this, I would take either zirconium or niobium, so either ZR or NB. But it's probably more likely to be zirconium only because the atomic mass of 90. See how that peak goes up higher to like 60%? See how it goes all the way up there? Most of it is isotope 90. So I would expect the average atomic mass to be closer to the 90 point. So 90 or 91, something like that. The fact that the 90 peak is so high tells me that most of it's 90, so the average atomic mass is going to be closer to the 90. So the most correct answer I would probably say is zirconium, but I get where you might say niobium as well. At least none of y'all tried to find 90 or 92 way down on the periodic table for atomic number, because that's not what that was asking for. Now, a lot of y'all are asking questions about things. Remember, you're going to get a copy of all this, and this is the kind of thing that you keep and you bring up to your teacher in the spring, or you bring up to your teacher tomorrow, hey, can you walk through this one question that I had yesterday? And they'll be happy to run through you, right? Okay. All right, so this is a question. I just want y'all to get a sense of, this is actually from 2000. So this is a former time, but this is what they're asking you to do. So you've got samples of natural selenium with 6 stable isotopes. Can you explain what the isotopes have in common and how they differ? So that would be one question. So they're asking, what do you know about atomic structure? So you ought to be able to look up selenium and know that they all have the same number of protons, and that isotopes are things that have different numbers of neutrons, but they would all have the same number of electrons. So that goes back to, do you understand what an isotope is? And then for part B, they're going to ask you to write a complete electron configuration. So no noble gas configurations for selenium. And then how many unpaired electrons are there, and explain your reasoning. So you can't just say 3 without giving some kind of an answer, right, of how you know that kind of a thing. And then for the very last one, they're asking you, why is the first ionization of energy of selenium less than that of bromine and greater than that of tellurium? So what I'd like you to do for us to kind of finish up our time together is find selenium on the periodic table. And find the other elements and see if you can figure out what would make them different, right? So selenium and bromine and tellurium. So on my periodic table, selenium and bromine are right next to each other. So what does that tell you? Well, when they're right next to each other, that means they have the same number of occupied energy levels. Don't say they have the same number of energy levels, because that's not true. All atoms have all energy levels. They may not have electrons in those energy levels. That's why it's important to say the occupied energy levels, or shells of electrons or layers of electrons. Use some wording like that that shows that you know what you're talking about. So selenium and bromine both have the same number of layers of electrons, are in the same row. That means we have to talk about protons. So selenium has 34 protons and bromine has 35. So that means that the one with more protons has a greater pull on the electrons. And that's why bromine has a greater first ionization energy and selenium has less. And then they want you to compare selenium and tellurium. So find selenium and tellurium. Notice that Se is above tellurium. So we're not going to be talking about protons right now. We're going to be talking about the distance of electrons from the nucleus. So remember, Coulomb's law is all about charge and then about distance. Well, selenium is the 4th row down in the periodic table. That means it has 4 layers of electrons or 4 occupied energy levels. Tellurium is in the 5th row, which means it has 5 occupied energy levels. Since tellurium's electrons are farther away from the nucleus, then that just means that the tellurium's electrons are going to be easier to remove because they're farther away. Farther away means less of an attraction, and less of an attraction means less energy to remove them. So I didn't say Zeph or any of the other things. You're just kind of stating what you know about the atom and periodic trends. Somebody asked how can you tell the number of valence electrons in the table? In general, you can take the group number and subtract 10. So carbon's in group 14, minus 10 would be 4. The reasoning for the number of unpaired electrons, Daniel Kelly from Carroll, is basically you just want to say things like, this is how many electrons. So selenium would be 4p4. So basically you're saying there's 4 electrons in the p sublevel. The p sublevel has 3 orbitals. So there'd be 1 electron in 2 of the orbitals, and 1 of the orbitals would have 2. Because the whole thing is each orbital gets 1 electron, and then you have 1 more to give, so you would fill 1. So basically you could either draw it out to show that, or you could explain it away just saying that when you put 4 electrons in 3 orbitals, 2 of them are half filled and 1 is filled. And it's okay to just say that. All right, so next Tuesday, and I would have given y'all more time to type out your responses, but I know, the goal was to be done in an hour. So next week, we'll be looking at Unit 2. Unit 2 gets into Lewis structures and a lot of that stuff, and like how do we know what shape it is and stuff like that. So come back next week at 7 o'clock. I'll be wearing a different hat and probably a different shirt. Hopefully I won't still be dressed like this. And thank y'all for coming, and I'll stick on for another minute if y'all have questions. JC, the recording of the meeting will be sent out by Matt Dean to the teachers. You're welcome, you're welcome, you're welcome. And if anybody has a question, feel free to unmute your mic or throw it in the chat, and I'll be happy to answer anything you got.
Can you explain C again?
Yes. So selenium has 34 protons, and bromine has 35. They both, if you did their electron configurations, they're all both going to be 1s2, 2s2, blah, 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 blah. Selenium is going to end with 4p4, and bromine's going to end with 4p5, like if you wrote them out. Since they both have 4 occupied energy levels, their valence electrons are both in the 4th energy level, then we don't worry about distance, because distance, who cares, right? So selenium has less protons than bromine. So bromine with more protons pulls harder on the electrons, which means it will take more energy to remove those electrons. More protons is more pull, more energy to remove them. So that's why bromine is more than selenium, or why selenium is less than bromine. In terms of selenium and tellurium, we don't care about protons. If you did tellurium's electron configuration, it'd be 1s2, 2s2, and it would end with 5p4. So tellurium's valence electrons are out in the 5th energy level. It has 5 layers of electrons. And selenium's electrons are in the valence electrons are in the 4th energy level. So which ones are going to be easier to remove? The ones closer to the nucleus or the ones farther away from the nucleus? And that first ionization energy is always going to be the valence electrons. So since tellurium's valence electrons are in the 5th energy level, that makes it less pull on the electrons, which means it's going to take less energy to remove them. So that's why tellurium has less of a first ionization energy than selenium.
So let me clarify. So if they're in different energy levels, it's more based on like the radius.
Correct.
And if they're in the same energy levels, it's more based on the protons and the pulling.
Correct. Because if it was always protons, then tellurium would win. But that's not true. Because it's based on the data, it's more about the radius. And if you look at Coulomb's law, that R is actually squared, so it's radius squared.
Okay, thank you.
Let's see. Oh, you're not Mr. Poe, by the way. Well, I just figured it was you. Do you have any advice that would be helpful with learning AP chemistry? You can do it on a block. So just because you got started in January does not mean you will get, you can't get through it. So there are a series of videos that your teacher can access through A+ College Ready. And there are a series of videos on AP Classroom. So if you go to AP Classroom, there are videos for every single unit 1 to 9. But when I taught AP Chemistry last year, and for 14 years before that, I always started in January. I could totally get through it. You can also look up Mr. Elegante's podcast. I have my own podcast. I don't know how great they are, but yeah. But just stick with us, because this is just identifying the stuff we're good at and identifying the stuff we need to work on. This is not to give you all stress, but to kind of just make you think, okay. All right, with that said, I think I'm all good. So if no one has any other questions, I'll go ahead and end the meeting for everybody.